Thanks a lot. So, since I finished last lecture with a little preview of the next lecture, let me start this one with a little reminder of the previous lecture. So, between saying what I will do and what I've done, maybe I managed not to say anything. So let's see what it was. So the idea was to discuss how, randomness comes from deterministic system, and I had this paradigmatic example of the Sinai-Bunimovic Lorentz gas. But of course, that is very technical, so it would take quite a bit to discuss that in detail. So I instead purport to discuss various ideas on how to obtain this type of result, but in a much simpler setting. So I started with the simplest possible setting, which is an expanding map of the circle. So I'll take it C2 of the circle in itself. So it is expanding, meaning that the derivative of the map is always bigger or equal than some lambda bigger than 1. And of course, this implies that the map cannot be one-to-one. So a typical graph will look like this. Maybe something like this. Okay. So this is a map with two branches, and it is always increasing. And of course, this is all mod 1. So it looks like 0, 1, but it is really on a torus. So the key feature of this map, of course, you can be upset because, the Lorentz gas is invertible, is an invertible dynamics. This is not invertible, but nevertheless, it has a very important feature that since the derivative is bigger than 2, nearby trajectory diverge at an exponential speed until at least they are close enough. So that is the key property that is used in the case of billiards in order to prove all the relevant results. So this map has this property. And that turned out to be the key factor somewhat. And studying invertible map, it is a little bit more complicated for some reasons that I will discuss in a moment. So, and we'll comment later on. So the basic idea is that one starts with a random initial condition. And I discussed yesterday a little bit what is the meaning of this random initial condition and what are possible alternatives to get almost sure results. But now let's just start with a random initial condition. So it means that the expectation of some function, so the dynamics, sorry, here the dynamic is xn equal fn x0. So you have some initial condition, and you apply the map n time, and this is the position at which you are at time n. And then I said that the distribution of the variable x0 is given by some density rho x. And I will require rho to be C1. This is not optimal, but it's okay. And I introduce a fundamental object in this game, which is called, it has bazillion of names. According to the people, it's called the transfer operator, the Ruel transfer operator, the Fredholm-Ruel transfer operator, whatever. It doesn't matter. I call it the transfer operator. So the transfer operator is just the dual to the dynamics. So it is defined in this way. If you have a function phi, which is composed with the dynamics, and then you have some other function rho, then by definition, this is the transfer operator. And it has a nice formula that I wrote yesterday. I'm going to write again, is the sum over the preimage, over the preimage of the density weighted by the derivative of the map. Okay. This comes from this definition just by changing variable. Okay. And I mentioned that a key factor in order to understand what's going on is the study of the spectrum of this operator. And the problem is that the spectrum of this operator depends drastically on the space on which it acts. In fact, I mean, like that is not even clear what I'm talking about, right? Because if you want to talk about an operator, you have to tell me on which space it's acting. Here, I don't say anything. But I mean, this is clearly well defined on L1 function, for example. But it turns out that if you, or L2 function also, it turns out that if you look at the spectrum of this operator on L1 or L2, then the spectrum turns out to be the full disk. And instead, the goal, as I said the last time, is to try to view this system as a Markov chain. So you would like to have something like a matrix somewhat, right? So you would like the operator to be quasi-compact. And it turned out that you can do a computation that shows the following. I mean, this is what I did last time. Oh, sorry. That this operator is a contraction in L1, and it satisfies this strange inequality in W11. So W11, I remind you that it is just the usual Sobolev space in which you take the L1 norm plus the L1 norm of the derivative. And then this is lambda minus 1, the W1 norm plus some constant and the L1 norm. Okay. So as I said the other day, these are Lasota-York inequalities. They were introduced in dynamical system by Lasota-York in the study of a more general system than that, but not so much. It was just an expanding map, but possibly with discontinuities. And they were motivated by some practical problem because this map was describing the motion of how it's called? I forget the word in English. Well, I mean, it is just an object to make holes, right, in the ground. So this is something that, it is something that looks more or less like this. Okay, and it rotates and it goes down and it makes a perforation in the ground. And the problem is that the invariant measure of the map describes the way in which these three objects are consumed. A drill, yes, that's correct, a drill, that's a drill. Right? Okay, so this rotates, it has three, and essentially what it does, it eats with one, and then, you know, it doesn't go down. It just eat, bounce, eat again, bounce, eat again, bounce, and like this, it just drills down. And the problem is that the invariant measure of the map is just describing the way in which these are consumed. So, of course, it is nice to have a rather flat, because if the invariant measure is not very flat, then it means that maybe these get consumed very quickly, and then you have to throw away this stuff, but there are still that are still good, right? So, and that's not very good if you want to save money. So it was a really engineering problem somewhat, but essentially it was boiling down to study the invariant measure of some expanding piecewise expanding maps. And so it was exactly the same. They got exactly this inequality, but of course, being in having a discontinuous map, the difference was that here there was BV instead of W11. Doesn't really make much of a difference. Okay, but in fact, as I mentioned yesterday, this inequality of this type were already known in probability under the name of Deblin-Forte, and they were used in some problem. I forgot which, but it was some study of Markov chain. I forget the detail now. All right? And the point is that since there is another basic property, the fact that the operator L going from W11 to L1 is compact. Okay, this just follows from the fact that the unit ball in W11 is compact in L1. And then it's possible to use a general theorem by Enion that says that then the operator L is quasi-compact, And in this particular case, with a little bit more work, you can show that there is the eigenvalue 1, that is simple. Then there is the disk of radius 1, on which there is the circle of radius 1, on which there is no other eigenvalue. Then there is a disk which is, let's say, of radius lambda prime for any lambda prime strictly bigger than, lambda minus 1. Maybe this I should call it nu. Okay. Some nu strictly, for any nu strictly bigger than lambda minus 1. This is a part of the spectrum that you do not control, and it can be essential spectrum. Actually, it's possible to prove that it is essential spectrum. And outside, there are only finitely many eigenvalues of finite multiplicity, okay? If there are. It may also be that there is nothing. Like, if, for example, if you take 2x mod 1, then there is nothing. If you take 2x mod 1, there is only this part of the spectrum that is essential spectrum, and there is 1, and that's it. But that is very special because 2x mod 1 is, of course, all linear. You can compute in Fourier transform, and then you see that there is nothing. Okay? But in general, there are eigenvalues. There are examples in which such an eigenvalue exists. So this implies that there is a spectral gap. And it has, as I mentioned yesterday, and maybe I was not very clear, let me just show to you that this implies some loss of memory. And so what I want to look at, I have two functions, f and g, okay? And I want to compute the correlation with respect to Lebesgue, let's say, right? Maybe I start with the initial measure. Okay? So this is just, with respect to the initial measure, is just phi compose fn times g. And I want to compute this correlation, and of course I can use the definition of the transfer operator to say that this is just ln g times rho. And now I have that the spectrum looks like this, and so it means that the transfer operator, it has a spectral decomposition, which is the projector applied associated to 1. It is just, so if I apply it to some function phi, this turns out to be just rho star, which is the invariant measure, the density of the invariant measure of associated to the system. So this is the unique invariant measure absolutely continuous with respect to Lebesgue that come from this picture, of course, because this means that rho star is invariant. If you apply L to rho, you get rho star. Then it is invariant. That means that this is the density of an invariant measure. And since you can prove that this eigenvalue is simple, then it means that there is only one invariant measure absolutely continuous. Sorry? Sorry, I didn't finish to write. 1 second. Yes. Then there is the integral of that, and then there is some operator Q applied to F. And the point is that the operator Q to power n in W11 is less or equal than some constant time mu to the n. And mu is this guy. Okay?
But you mean absolutely continuous?
Yes. Absolutely continuous invariant measures. There is a little bit subtlety here because, of course, you can say, no, you are cheating because this just proves that in W11 there is only one invariant element. Okay, so maybe there is some other measure that is invariant and is absolutely continuous and is not in L11. But it is kind of nonsense because you can, since you have this inequality, it means that you can approximate any function that is in L1 by a function that is in W11. You make a mistake, this mistake will stay small, and then you apply this business, and then you get the same result. So it is possible to show very easily that, in fact, there is only one measure that in L1. So that means that there is only one measure that is absolutely continuous with respect to Lebesgue. And there is the density is rho star, and the density is in W11. So you know that is, actually you can prove that is even smoother, but I mean, that's what I have at this point. So okay, now you want to compute this correlation, and then you have that, and now so you use this spectral decomposition, and so this means that you have phi times rho star, and then it's multiplied by the integral of G rho, and then there is the rest that is of order mu n. Okay? Provided, of course, that this, I mean, this must make sense, no? So it means that this stuff here must belong to W11, and this stuff here must belong to the dual of W11. So let's be just simple. Let's say it belongs to L infinity, it's fine. It can even be wilder. That's not a problem. But provided that is in the dual of W11, then this makes sense, and you get this result. Okay, very well. So this, what does it mean? It means that you start with, okay, this is mixing, right? Because if you take the case in which G is 1, that means that you start from an invariant a measure that is not invariant as density rho, and then you tend to the invariant measure exponentially fast. So that is, yeah. Oh, sorry. You are right. I mean, yeah, new one, let's say. Okay, that is just the spectral gap. So I'm sorry. Yes, that is just the gap between the first and the second eigenvalues that must exist because the operator is quasi-compact. Okay, so that is more or less where I end up yesterday. And so it's clear that this is looks very nice because now you have some sense in which you lose memory. Of course, if you are so crazy, like to start from rho that is a delta function, so it's very far away from being W11, then you won't see any loss of memory whatsoever. That's clear. But so it looks very much like a Markov chain. The only real difference with the Markov chain is that for a Markov chain, maybe you have this exact statement, but only for all function in L2. And this, for all function in L2, is simply false. Okay, so you just need to deal with to live with the fact that you need some regularity in the business. Apart from that, the logic is exactly the same. Okay, so now let me take a function phi such that is zero average. So this is a zero average function with respect to the invariant measure. And now I want to study this quantity as I discussed yesterday. Okay, so this is just my random variable is just my observable at time I, which is given by phi compose the dynamics. And, or if you want, you can write this like that. It's the same. Okay, this goes like that. And so this is my random variable, and this is zero average. Okay, so this is stationary. So these are a sum of zero average random variable, and I would expect this to go to Brownian motion. So let me just start to look for simplicity to the case t equal 1. So that means that I'm just looking at, let's call this just z epsilon is just epsilon sum over I that goes from 0 to epsilon minus 2 of phi xi. Just to start, let's look at this. So this should go to a Gaussian. Should converge to a Gaussian weakly. So this is a random variable because the x0, the initial condition, is random. It's distributed according to rho, to some measure rho, absolutely continuous with respect to Lebesgue. And now I want to know what happened here. Okay, so there are, as I mentioned in my preview yesterday, several ways of trying to establish this result that are shamelessly copied from probability. So let me start with the first one, which as far as, I don't know, as far as I can trace it back, it is due to Gordon in 1969, but I don't know, maybe it has been done before, but at least this guy is Russian, no? So, I mean, the Russian cannot say that they did it before. He was Russian already, so okay, fine. But in any case, he's still Russian. Okay, I'm sorry. He's alive? I didn't know that.
Yeah.
Okay, okay. Well, I never met him. Okay, so thanks for the comment. All right, very well. So the idea is to do a martingale approximation. So well, how does it go? So if you want to talk about martingale, of course, you have to talk about sigma algebras. So you start with F0, which is the Borel sigma algebra, and then you map it with the map, and then it is sorry, I'm going to have to go backward or forward. No, I have to go backward. Yeah. So that means that this is a rougher sigma algebra, right? Because you see, if you take some interval here, then the preimage will consist of two guys. So you see, so you have that the element of F1 must contain pair of intervals that are mapped to the same, right? So this is a rougher, rougher sigma algebra. And now you want to compute maybe what is the expectation of a function phi with respect to F1. And then if you want to do that, maybe one way is to just compute G compose F of phi. Okay, so this is like, now this is measurable with respect to this sigma algebra, so this is just Z. Okay. On the other hand, this one, you can use this thing here. That's the transfer operator. So let me just imagine that I start, let me simplify things. I start with the invariant measure. Okay, so I start with the invariant measure, so this is the expectation with respect to the invariant measure. So this will be, okay, let me make a little comment about what happened to the operator L. Because the operator L, you see, depends from the measure. See, this is the transfer, this formula here is good for Lebesgue, right? You do another measure, you have a different operator. So, but if it is absolutely continuous, it's kind of obvious, because you have phi compose F, G, rho, and now you want to see, this is just rho star, sorry. So this is just the expectation of this quantity with respect to the invariant measure, and now you want to see the dual. So you work with respect to Lebesgue, so this is L, G, rho star, and then you want, that is with respect to the invariant measure. So you just see that the operator with, I don't know, let's call it star, with respect to the invariant measure applied to a function g is simply 1 over rho star L G rho star. Okay, so that is, but this is, and of course you have to check that this is never 0, but this is kind of easy. So this is strictly bigger than 0, rho star. So that means that this is a very well-defined new operator, and it's conjugate. This is a conjugation, right? So this operator is conjugated to this, so it has exactly the same spectrum. So I will just suppress the star and don't worry about it anymore. Okay, so I have this now, and now I can write this as G compose F just because of invariance. And since this is true for each G, then this must be equal to L phi compose F. So that I have some formula of the conditional expectation in terms of my transfer operator, which is kind of convenient because I control the transfer operator while the conditional expectation I don't know exactly Sorry? The filtration is decreasing, right? So the F0, this is kind of, I will get a reverse martingale rather than a martingale. Because I start from Borel and then I apply you see. So this, take any Borel set here, the pre-image is given by special Borel set. Because if there is this one, then I have to go here and I have to have also this one, right? So if the map was not reversible, this idea is nonsense because I get just the image of the Borel set is the Borel set, right? So I don't get any, that's why I'm talking about non-invertible, it's easier. If you have to talk about invertible, you have to be, essentially what you have to do, you have to put by hand some sigma algebra that is not Borel and that behaves in the right way. So it's possible to do it, but it takes a little bit of more. I will talk about that maybe later. Yeah? Yes? No, that's what Stefano was saying. If you don't have several pre-images, F1 is equal to F0.
Okay.
Yes, that's what he was complaining about, that this works only for non-invertible maps. Okay, for invertible maps, I will have to do something slightly different, but one thing at a time, right? So you are ahead of myself. I mean, I don't know how to say it. Yes. Sorry. I lost the chalk. Yeah. Okay. So now we have that. And now there is this idea, and the idea is kind of, I don't know, it's kind of an idea that is kind of pervasive. You want to write some martingale, so you have to solve some kind of Poisson equation, something like that, right? I mean, that is, yeah, whatever. So, I never remember. Okay, so let's say that I find the G that satisfies this equation. Imagine that I can find the G that satisfies this equation. So this is my equivalent of the Poisson equation, right? I mean, this, yeah. If this were a Markov chain and this was a self-adjoint operator, then I would be copying Kipnis-Varadan, essentially, right? Okay, so, but this is not self-adjoint, so I need some information on this operator. Okay, but now I imagine that I have that. So now I want to introduce my object, which is, sorry, I have to copy because every time that I do this computation, I mess it up. So I just wrote it, hoping that I wrote it properly. And now the point is that you want to compute y with respect to f1. Okay, and now, since I have that formula, that means that this is L phi compose f, okay, and minus L, sorry, it's L phi compose f. Okay, so I have to apply, first I have to apply f, so I will put the composition with f outside everything. So I have L phi z minus Lg minus Lg compose f, and then f is compose f. Okay, I just applied my definition, my formula for the conditional expectation. And of course, the point is that if you look at the formula here, you will see that if you apply this thing to a function compose f, then f of y is equal to x. So it means that this is just phi, because this is just f composed on the preimage of the point, but that is the preimage of the point is the point of, the image of the preimage is the point itself. So this is phi, and then there is this operator applied to 1. But this operator applied to 1, it is equal to 1 over rho star L rho star, but since rho star is the invariant function for this operator, this is rho star over rho star, which is 1. Okay, so this operator with respect to the invariant measure fixes 1. So I get here this, and then I get minus, oh, sorry, here I have a wrong sign, of course. This is a plus. And then here again, by the same argument, I have plus G, compose F. But this satisfies this equation, and so this is 0. So it means that F is Y, when I condition with respect to F1, it's as 0, so is exactly 0. So that, and by a similar computation, you can see that if you define yi equal y compose fi, then you have that the expectation of yi fi is 0. So that means that if you take the sum, you get a martingale. So where do I write? Here. Okay. So I now take, what I am interested in is epsilon I that goes from 1 to epsilon minus 2 of phi compose fi. And now I just this goes to from 0. Okay. And then I just put this, and then I have to subtract what I added. So that is minus G composed F. G composed Fi minus 1. Sorry. What did I do? Sorry. This is, yeah, plus G composed Fi. Okay, so this is, let's rather the sign are the opposite, okay? So this is just that, and then I have some boundary terms, because the first one and the last one are kind of messy, so this is just order epsilon. And now, of course, this is telescopic sum, so that means that when you sum this up, you get something of order 1, so that also is of order epsilon, and then you end up with that. But this sum is a martingale, because when you just make the expectation with respect to the filtration, you get 0. So these y are just a reverse martingale difference. And so you can use the central limit theorem for martingale. And that's the end of it. That's the idea. And so what you have to choose. So all this is based on the fact that you can solve this equation, right? And G, which is the object that appears here, should be a function that is at least in L2, because otherwise your martingale is not in L2, doesn't make much sense. I mean, well, maybe you can actually exactly using a trick like the one in Kipps-Silvarad, and you can go a little bit beyond L2, but I mean, you need some information, right? Otherwise, it doesn't make any sense. So, but in my particular case, everything is very simple, because look here, I want to solve this equation, and of course, this is 0 average, so I can assume without loss of generality that G is 0 average. So that means that when I look at this equation, I can write it as phi, and now I have to apply this L on G, but L, it is, well, now is not this L, but it's this divided by rho and multiplied by rho. So there is a rho here. So it means that this applied on a 0 average function, this part you don't see, you see only that. Okay, so it means that this equation for 0 average function becomes this. Okay. Okay? But now this guy is, if you live in the space of zero average function that is invariant, so this you can restrict to that space, and on that space, this guy is correspond to this part of the spectrum. It's strictly less than 1. So this makes perfect sense to invert, and you get that G is equal to 1, well, minus G actually, minus 1 minus Q minus 1 phi. This is an element of W11. Because the operator is invertible now in W11. So it's just kind of trivial. But of course, it rests on the fact that you have this rather detailed understanding of the spectrum of the operator. So, okay, so this is this possibility that since here almost everybody, I guess, is a probabilist, then I won't, of course, explain the martingale central limit theorem that I just used. Okay, and then modulo that is a proof of convergence to CLT. Okay, so second trick. So this is just, what time is it? You see? Yeah. Second trick. So the second trick, I do not really know who really invented it first. I mean, I learned it from the work of Guivarch, that is French, okay, but I'm perfectly willing to imagine that it has been done by some Russian before. I don't know. Guivarch told me that, yeah, the idea was more or less around, but I mean, in any case. So what is this idea? This idea is the following. You want to compute, want to show that this stuff is going to be a Gaussian random variable, and what do? You just compute the characteristic function. So you compute the characteristic function, and you try to compute the limit for epsilon that goes to infinity. If this limit for epsilon that goes, epsilon that goes to 0. If this limit exists and is a Gaussian, then, I mean, is the Fourier transform of a Gaussian, which, by the way, is a Gaussian, then you have proven your result. Okay. So this is the goal. And the trick consists in the following. You just look at that, and you just say, OK, this is IXC. You expand it. And so this is just some epsilon, sum for I that goes from 0 up to epsilon minus 2 of phi composed F. Okay, and now you just write it in a slightly different way. You write this, this is I, okay? And then you take one term out. Okay, fine. So this, you can write it then as e to the I c epsilon sum from I that goes to 0 to epsilon minus 2 minus 1. Actually, probably this, if, here actually there is a minus 1 normally. It doesn't matter. It's just an irrelevant difference. Now this is minus 2, and this is phi, compose fi, but now everything is composed by f. And then you have e to the I c epsilon phi. And now you apply this transfer operator. I mean, this, at the end, this is always the idea. So you get e to the I c epsilon sum I from 0, epsilon minus 2, phi compose fi. And then you have L e to the I c epsilon phi. And now you look at that and you say, OK, but what about if I define this operator? Okay, this new operator, it means that it's the normal transfer operator, but before applying the transfer operator, you multiply by this complex phase. Okay. But then this, it is, you can see it as this operator LC applied to 1. But then you can do this computation again. I mean, you just take another term out of the sum here, as I did. You push the transfer operator over there, and you get another one. So eventually, you get this form. Because it's always the same. And next time, you pull out another factor, which is the factor 0, and then you take the transfer operator, and you get again LC, so you get LC squared. Okay, so why is this nice? Well, it is nice because once you notice this, then you see that understanding what happened to this characteristic function is tantamount to understanding what happens to this transfer operator. You have to study the spectrum of this guy. But the spectrum of this guy is not so far away because epsilon is small. You are interested in Xi, maybe of order 1 or maybe a little bit bigger, but I mean, the Xi can also increase by epsilon, but I mean, you, unless, if you want to look, at something that doesn't get quite to the local CLT, then you are interested in Xi that are small with respect to epsilon minus 1. If you want to get to the CLT, then you have to know something about this transfer operator. For the local CLT, you have to know something about this transfer operator for Xi that is of order of epsilon minus 1. So this is outside perturbation theory. You have to do something. But if you don't want to push it till the local CLT, then you are just interested in Xi that are kind of, let's say, Xi epsilon smaller than delta. And that means for some small delta, and that means that here, this quantity is small. So you are just looking at a small perturbation of the operator L. So it is kind of reasonable that you can compute stuff by perturbation theory. Then you compute by perturbation theory, and you look at the maximal eigenvalue, because how will this grow? This will grow with the maximal eigenvalue of this operator. Because this is a small perturbation of an operator that is quasi-compact, so you expect it to be quasi-compact as well. So everything is reduced to perturbation theory. So you have to compute stuff like LC of G is equal to sorry, you want to find the maximal eigenvalue, so let's call the maximal eigenvalue, I don't know, V, so this is Vxc, and then it will be lambda Xc, Vxc, okay? And notice that this operator is analytic, right? Because you can expand in series this stuff. So this is an operator that is analytic in C. So this is just analytic perturbation theory. You open a standard book, like Cato, for example, and it tells you that everything is okay. The eigenvalue are the spectral data are analytic in C, so it means that the eigenprojector of this eigenvalue are analytic in C, but this guy is simple, so the eigenvalue itself is analytic in C. So the eigenvalue is analytic, the left and right eigenvector are analytic, everything is analytic, so you can take this information from Cato book, for example, and then forget about all this stuff and say, okay, then I just do what every physicist do. I just take this and I differentiate and I compute. I can differentiate. So if you differentiate, what do you get? Let's compute the first derivative. So the first derivative, I have to take the derivative with respect to C of this operator, but the operator, that's just this. Okay, so if I take the derivative with respect to Xi, then I get L Xi times I epsilon phi applied to V Xi plus L epsilon vc prime is equal lambda epsilon prime vc q lambda, sorry, epsilon c, and then this is lambda c v prime c. Okay. And now, of course, you have this is the right eigenvalue, you have the left eigenvalue. Okay. This is the left eigenvalue, so if you hit this stuff with the left eigenvalue, then you will get E epsilon LC phi VXC plus here you get lambda C L C V prime C, and this is equal to, now of course if you want that the projector is made by the left eigenvalue and the right eigenvalue, then of course you have to normalize stuff in this way. Okay, this is just a normalization. So when I hit this guy, I get 1, so lambda prime c plus, and here I get lambda c L c v prime c. The prime, of course, is the derivative with respect to c in this case. So as you see, this and that cancel, and then I get this formula. I get, so sorry, I maybe should have been more precise since I put up the name before. I should put up the name now if I find it. Where the hell is it? Here. Yes, so this now is here. I never know how to spell this guy. And this is, at least that is where I learned this trick. And okay, then you get lambda prime c is equal to I epsilon L epsilon phi VXC. So you get this formula here. It's the usual formula that you get for in perturbation theory. So this, every physicist knows it by heart. And the point is that if you take the derivative at 0, then you get I epsilon. Then this one turns out just to be the Lebesgue measure, and this is just rho star. So you get phi rho star. But since this is 0 average, this is 0. Okay? So it means that the maximal eigenvalue of this operator in first approximation, it is just the derivative is just 0. And of course, so now what it means? It means that this is lambda c is equal to, well, there is 1, which is the value of the eigenvalue when xi is 0. And then the next term will be, well, you have to take, how do you compute the next term? You have to compute the second derivative. So you have to compute the derivative of this, the derivative of this. It's a little bit boring computation that I spare you. Yeah, I spare you because it's kind of boring. But I mean, essentially, what you will get out of the derivative another epsilon, because when you take derivatives, I mean, each time you will get an epsilon, so you would get epsilon squared, then there is I squared, because that is a minus. So you expect that this will be something like sigma square epsilon square, and then there will term in epsilon cube. Okay, that's what. And now you would like to know what sigma square is, so you have to do a little bit of computation, find the formula in second order, and blah, 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 and surprise, it is the variance. Okay, what can it be? So it is the variance of phi with respect to the invariant mesh. Okay, I don't, so now what I do, I just say, okay, I do a small, epsilon is kind of smallish, so it means that this spectrum will change, but this is a gap of order 1, so the gap will survive. And so I will have for this operator the same spectral decomposition that I had for L when xi is equal 0. And so essentially I will get that this I can write it as like as e to the minus sigma square, oh sorry, there is a xi square. Epsilon squared xi square. And plus higher order term, which can be computed, right? If you are really, for example, with this technique, if you want, you can try to get an Edgewood expansion. I mean, that's perfectly possible. But, I mean, let's just keep it simple. And then what do you get? You get that this will be like the maximal eigenvalue to power epsilon minus 2, xi, okay? And then there will be some smaller things that it doesn't matter, because this decays exponentially, right? So essentially, this will be that. And this one, now I know this expansion, it is just e to the minus sigma square xi square. Maybe you want to write 1/2, I mean, traditionally. There is 1/2 that comes from the fact that this is the second order expansion, right? So you want to keep it. And this is the characteristic function of a Gaussian. So that means that when epsilon goes to 0, this stuff converges to this stuff. And if you keep track of the mistake, you can keep track of the mistake pretty well. So this trick, when it works, it is very, very efficient because it gives you a very quantitative information about what's going on. Okay, and so again, another time you have obtained this central limit theorem. Okay, let me just get, yep. So let me just get to the last trick that I want to discuss. So essentially, in order to do this game, I know really kind of 4 tricks, yeah, I think. So 2 I said, 1 I will discuss, and the other one I will not talk about because it is useful only in a little bit more complicated situation, and is based on rough path theory, so it will take a little bit longer to explain. Also because I don't understand it very well, so I'm kind of ignorant. That, of course. All right. So for this last thing, let me just be a little bit more ambitious, because maybe some of you is a little bit kind of getting a little bit annoyed because they say, okay, but you were talking about convergence to Brownian motion, but you have just talking about just one marginal, right, that converges to Gaussian. Of course, then I could, with the same technique, study higher dimensional marginals and then do some compactness argument or whatever. But it would be nice to have a technique that attacks directly this quantity and shows that this quantity converges to a Gaussian, right? So there is a little bit here, in order to be careful, there is a little bit something that I should mention, the fact that this sum here, it doesn't make any sense, right? Because this should be an integer, and this is not always an integer. So I should put here something like this. Maybe that would be better, at least now the formula makes sense. But this has the problem that it is discontinuous, right? Because it jumps when t moves by epsilon, it remains constant, and then it jumps because you sum one extra term. So it's perfectly okay. These paths are discontinuous. That's fine. The only price that you have to do is that you have to use the proper topology, right? Like Skorokhov topology, or maybe you have to talk about Cadillac function if you are French or something like that. But the problem is that I prefer avoid that essentially because I never learned how to spell Skorokhov. And so I think that I would like to have it continuous, right? And to have it continuous is just simple. You just make a polygonalization. So it means that, I mean, this is the epsilon, okay? And then this is like epsilon, 2 epsilon, 3 epsilon. And this sum here it's something like that. So here it is like that, and here it is like that, and here maybe it is like that, and like that. And what I want to do instead, I want to do this. Okay, so I just take, I don't know, like the first value, and I just interpolate the points here by a polygonal. So the mistake that I do is trivial, right? It's just order epsilon every time. So it doesn't make any difference. So I just will consider this continuous path that is obtained by the polygonalization of the sum. So now this, it belongs, let not me write it because it's kind of, okay, I mean, you can write a formula, but this is the formula. So let me just assume that we understand what we talk about. So now this, it is an element of C0T, and it has value in R, let's say. Let's say that I am in R, so I take the universal cover of the circle, not to worry about this mod 1 business. Okay, very well. So now I have such a path in C0, and since I have my initial condition that is random, for each choice of the initial condition I have a different path, and this means that my random initial condition induce a measure on C0, which describe this path. It's kind of very singular measure, because if you tell me the first point that everything else is fixed, but still is a measure on C0. And now you can wonder about what happened to this measure in C0 if when epsilon goes to 0, if it converges to something, hopefully it will converge to Brownian motion. That is what you want to prove. So you want to prove this is a random variable in C0, and you want to prove that this random variable converges to Brownian motion. So this is a technique that has been kind of, is getting closer to this paper of Bunimovich and Sinai, but they started the business, right? So afterward, there were some more ideas that made the business a little bit simpler, and so that is what I would like to talk about. Yep.
Why doesn't the martingale method already do it?
The martingale, I didn't understand.
Martingales, you have convergence and in motion.
Yeah, you can do it also with martingale. That is correct. I mean, with like the Gordon trick. Yes, but the problem.
You need to control the supremum of these things.
Yeah, that is true, because these are bounded things. That is absolutely true. You can upgrade the first thing that I said, Gordon, to this. But this technique that I'm going to discuss is, in fact, very similar, but it has some advantages that it is extremely flexible, and it can be applied to much more complicated systems. So in principle, you are right that since I'm discussing a very simple system, then most of these techniques collapse to the same thing, more or less, right? But they are different point of view, and in different situations, they have advantages. So that's why I'm just trying to present different point of view. I understand that from your standpoint, it's all the same, but yeah, there are some. Okay, so this, in fact, you are actually right. This is kind of another martingale idea. But what it was done, so this was due to, essentially in the form that I am presenting, it is due to Dolgopiat, and it is kind of more recent. Now I forget to write it, but it is already this millennium, so it is kind of. So the basic idea is the following. I mean, first of all, you want to look. So the idea is the following. First, you want to show that this is tight. Once you show that this is tight, then you can try to identify the limit. So this is kind of standard approach for these things that is used normally in probability. And the idea is to just implement the same type of thing in this case. And what I want to do, well, I want to compute this quantity. I want to compute the force moment, because if I compute the force moment and I get a good estimate for, how much the increment, then I can try to use Kolmogorov criteria to say that the sequence is tight. Okay, so, okay, I want to compute this first moment, so let me just show you this computation. This is always the same. So this one is a sum, okay, that goes from two places. So what I will get? I get epsilon to the 4. Then I will get the sum on I1, I2, I3, I4. That goes essentially from 0 up to epsilon minus 2. That's just me a little bit, I mean, minus 2, minus t. Okay. This is kind of irrelevant. Ah, sorry. No, this is relevant. Because I'm just going from t to t plus h. So that means that this index, they go from epsilon minus 2t to epsilon minus 2 t plus h. And then I will have the expectation of, so what am I summing? I'm summing this stuff. So it will be phi compose fi1, phi compose fi2, phi compose fi3, and phi compose fi4. Okay. It's I just wrote the sum. And now you see what you need again is decay of correlation, multiple correlation, of course, no? Because I showed to you at the beginning, now I see that I erased it. Yeah, I erased it. That, I mean, you have decay of correlation for two functions. But the same trick works to show decay of correlation of multiple functions, because you start to, you know, put the transfer operator, you put it there, then the transfer operator kills everything but the part that project on the invariant measure, and then you get a thing with three functions now, and you go on. So it's a complete, it's the same computation that I did for two functions, but it's done for all these functions. So that is perfectly okay. You have just to, see, there is something that you can worry about. No, you don't. In this particular case, you don't have to worry about anything, because the decay of correlation work provided that the function on the right of the, so let's say that this is the biggest one. So you put the transfer operator here acting on this stuff, right? Now, this is perfectly, no, you have to do it. Yeah, this is perfectly okay, but then this one you can be a little bit worried, right? Because the derivative is huge. Okay, so that means that you have to start from the small one. Okay, if this is the small one, then you apply it over there, and then everything pops out actually from the transfer operator. So there is no particular problem. You have just to apply the same formula and compute. So what happens? It happens that this one, it will be always small if two of these if all of them are different, then it will be super small. So the only possibility for this to be of order 1 is when all these are equal, but these are very few terms, like these are just epsilon minus 2 terms. Then there is the possibility in which these two are equal and other two are equal. That is okay, because then if two are equal, then you are looking at phi square, and then there is another phi square, so these are not zero average anymore. Because the problem is that if one time is different from the other, then just by decay of correlation, you get the average of this time that is different, and then you get 0, because this is zero average. So the only way to form stuff that is not zero average is that if you have a phi square, phi cube is not, also phi cube is okay, but I mean, but then no, phi cube is not okay, because then you have one phi alone, and then that will give you 0. So this is like, essentially, think about independent random variable is the same computation. So here there are only essentially epsilon fourth term, right? Because the only term that give a contribution is when you have a square. So when you have a square, so they are terms like this. And maybe A3 is equal to A1, and A2 is equal to I4. Okay? these are terms that give a contribution. They give a contribution of order 1, but they are epsilon to minus 4, this term. So you have epsilon to the minus 4 term here, you have a mass of 4, so this is, so they are, sorry, how many they are? Yeah, they are epsilon to the 4, epsilon to the minus 4h squared. That's how many they are. This goes, epsilon minus 2h is the number of terms that you have. So this is epsilon h squared times some constant. So that means that this force moment is controlled by the size of the increment to power 2, and this is enough to apply Kolmogorov criteria. So this, did I? Sorry. Yeah, I'm sorry. I start to be tired, so well, it doesn't matter. I do mistakes also when I'm not tired. So, okay. So that is fine because you do this computation and you show that now you have a tight sequence. So you can get convergent subsequence. All right. So now you get convergent subsequence. And what do you do with convergent subsequence? So the basic computation is the following. Let me just, this computation is not enough for what I want to do, but at least it shows to you what the idea is. So let's take some function phi, which is, I don't know, like C2, maybe C3. Let's be generous anyhow. And now I look at phi of the epsilon t minus c, t plus h, sorry, minus phi of the epsilon t. I want to compute this quantity here. So I want to compute this quantity, what do I do? Well, and then of course I will look at it in some sequence epsilon j that such that is converging. So, but now let me just compute this quantity, and then I will look at it along a convergence subsequence. So if I take this quantity, of course, what I have to do is just expanding in series. What else can I do? So I expand in series. Sorry? No, you can, whatever, an invariant beginning invariant measure that is absolutely continuous with respect to Lebesgue, and this is smooth, this will be okay. Yeah. So it is just, I mean, you can do it with respect to the invariant measure, but there is no reason to do it. You can just take exactly this setting. But if it is invariant measure, it does not depend on t, right? But still depend on h. Eh? Yeah, it's constant in time. That is correct, because it's kind of completely stupid at the beginning of the invariant measure, but it's just an increment, right? So it will just depend from how long you take the increment. I mean, it depends on age. Yeah, I mean, since I start not necessarily from the invariant measure, I start from some distribution, then it will not be stationary, right? At the beginning, something happened, but very quickly I will go, since it goes to the invariant distribution exponentially fast on this time scale, I'm always, I'm immediate in the, so in fact, at the end, it does not really depend on t. But, okay, so, but anyhow, I mean, what do? You just write this as the expectation with respect to psi prime z epsilon of t, and then you have the difference. And then you have the next term. times the difference square. And then you have the next term. But since the next term will have this to the cube, right? But this function is bounded, then it means that the next term will be bounded to the cube power of this difference. But since I just proved to you, sorry, I erased it, but I just proved to you that the first moment is uniformly bounded then by h squared, then you can apply Holder inequality and you get that this is of order of h to the 3 half. Okay. So it's a little bit smaller than h. Okay, and now you have to compute this stuff. Okay, so again, to compute this stuff, you can apply again the transfer operator because this one is a sum of, so let's look at this term, for example, right? So let's look at this term. So this is phi prime of the epsilon of t. And then I have the sum for I that goes from where there from I erased it, of course. So from epsilon minus 2t to epsilon minus 2t plus h of what I'm summing. I have epsilon in front, and then I have phi compose f I. Okay. So the point is that this is the function that depends from time. So maybe it's better to write it like that. Let's go from 0 to epsilon minus 2h, and this it is I plus epsilon minus 2t. Okay. So the point is that this function depends from the time before that, and so this is an extra time. So you have again, you need again decay of correlation because this is something at time t, and now this variable instead is a much later time. Well, much later, depends, but so it is. You have to do this computation. You can do it with transfer operator. It's okay, but there is a slightly better way of doing it, which I'll describe in a moment. But the point is that it's not so surprising that the result that you obtain, it is just something like that. Essentially, it's just a decay of correlation. And then there is the expectation rho star phi, and then there are small terms. So this is 0 because phi is 0 average, and then this is a converging sequence. So this is also of order epsilon. So this term here is of order epsilon. Okay, and now you have to do a similar computation for this term, and of course you get the variance here. So essentially, the result that you get is that when epsilon goes to 0, okay, this then you have that your z epsilon j will go to some random variable z, and then the random variable z will satisfy the following equation: psi z t plus h minus psi z t is equal to the integral of 1/2 psi second derivative z of t times sigma square h plus order of h to the 3 half. So the limiting process must satisfy this, and then if you take essentially the limit h going to 0, that tells you that the time derivative here should be equal to this stuff. So you can turn this into a martingale problem, and it has a unique solution, and the unique solution is Brownian motion. So that is essentially what eventually we will get that psi z t minus 1 sigma square half the integral from 0 to t psi second z s es. Okay. I mean, in principle, you want to show that this is a martingale, right? And then this will show that the limit identify uniquely the limit. There is some problem, of course, in what I just said, that in order to show that this is a martingale, then you would have to prove this, not this what I did, but this condition to the sigma algebra at time t. Okay? That's what you really want to prove. And in order to do that, you have to multiply here by functions that depend on smaller time and redo the same computation, which is kind of. But this is an important fact, because this is what, so this is just the idea, essentially. This is no different from what you do in probability. Although maybe in probability, I mean, this is kind of, how to say, a poor man version of what people do in probability, because in probability there are kind of fancier tricks to get the martingale, and here you just, you know, like, you just compute by brute force, and you see what happened to the generator. You're just computing the generator of the process, essentially, right? So you just do it by brute force and you compute. But the point is that there is this non-trivial problem that is conditioning. Because you want to obtain this result. Yeah, you want to ask something, Stefan? You are thinking if you want to ask something, yeah. Yes? Still, the problem is that you have always to keep in mind this fact that decay of correlation is in this weak sense that is only for certain observable. And there are dangers, right? Because look at this guy, for example. This guy is okay if it is on the left side of the transfer operator. But but this guy is a problem in principle. Because when you apply the transfer operator to this guy, then inside you have, in here, you have like phi to some f to some I power. And the transfer operator acts well on functions that are in W11. But now try to compute the W11 norm of this guy. This is huge. It is of the order of lambda to the k. So you have to be extremely careful, because the problem is that now why you are safe? You are safe because this is a transfer operator at an even larger power. And you have this Lazotta-York inequality. Each time the L1 norm goes down by lambda minus 1. So if you have something that is as a norm lambda to the k, and you apply more than k power of the transfer operator, still you can be safe. But it's not completely, I mean, you have to be careful. I mean, this fact that you get decay of correlation only for certain function of some regularity may seem very innocuous. But then when you start to compute, it can create a lot of problems. So these techniques essentially are developed in order to circumvent this difficulty. There is a difficulty that is this one, that you have some limited control on decay of correlation, and to circumvent it has been invented all kind of machinery that is kind of. So in particular, I mean, one way of dealing with this thing is that now you would like really to take conditional expectation. And now, of course, conditional expectation, it is a problem. Because you cannot take really conditional expectation. If you are so crazy as to condition exactly on the sigma algebra, then you risk to just don't see anything, because you tell me exactly in which point I am. And if you tell me in which point I am, it's a deterministic system. The probability is gone. There is no probability anymore. So you have to invent some mechanism whereby you can do something. I mean, this also, I don't know. I mean, of course, I'm not a probabilist myself, but my impression is that from the probabilistic point of view, if you cannot take conditional expectation, then you should feel a little bit uncomfortable somewhat, because that seems that is kind of that you do all the time, right, taking conditional expectation. So this fact that is you cannot take conditional expectation is something that it will be nice to circumvent in some systematic way. And the way to do so, there is a very nice way of running around to this problem that is due to Dolgopiat again, and is called the standard pair. So let me just tell you one thing about this standard pair, so you can see how this game is played. Standard pair are, by the way, an alternative manner to get this type of result, although much less precise, the type of result that I get, like decay of correlation. The problem is that you get, with this spectral technique, you get much precise result. With standard pair, you just get decay of correlation, but the standard pair is much more flexible. Actually, I like it very much because it is really kind of a super minimalistic approach to the problem of studying decay of correlation. You just use exactly what you need and not a iota more. So this is very good if you want to attack more complicated system, right? There is no Banach spaces, there is no fancy inequalities, there is nothing. It's just based on the idea that you use a certain class of measure. This class of measure somewhat is invariant under the push forward of the dynamics, and then you do some coupling argument if you want to show that you have convergence to equilibrium. So in this particular very simple case, a standard pair works like this. You just define some scale delta, you choose delta, and now you consider measure of this type. So you are on a circle, right? So of phi of x, and then you have some rho x dx. Okay, so it's just, and rho x over rho y is s or equal than e to the a x minus y. So the standard pair consists of the interval a plus delta and this density rho. This defines uniquely a measure through this formula. Okay. I think that originally when Dolgopiat introduced this, he called them Markov family because they do have some kind of Markov structure. But then I complained with him very bitterly because at the time I was kind of in a crusade to avoid Markov partition, so I didn't like anything that had the name Markov in it. And somewhat he somewhat, I don't know, was maybe thought that it was a reasonable complaint, and then he called them standard family, and the name stuck. So now they're called standard family. But the reason why there is some, so this you see, it just means that you are just taking some very special class of measure. The density is as the logarithm that is Lipschitz, of constant Lipschitz A. Okay. And the basic observation of Dima is that, well, this actually was already, in some sense, was already present in paper by Sinai and other people. I don't remember, but do you remember what is this paper in which they construct the SRB measure pushing leaves? That was Sinai and someone else. I don't remember what was that. But anyhow, I mean, anyhow, it's Russian school. I mean, so Sinai was the advisor of Dolgopiat, so it's kind of all in the family. And now the basic idea is that now look at what happened at the push forward of this measure. Okay. So the push forward of this measure, what it will be? It will be the integral from a a plus delta, and then there will be phi of x, phi of x, and then you have rho of x, right? Dx. And now you just change variable, and let's imagine that this delta is very small, so now this is locally invertible. So there is an inverse, because if this is not invertible on the whole, but if you just take some small interval, then it is invertible. I mean, so there is some invertible thing. And so then you have that FA, you have an interval, FA plus delta. And of course, this interval will be longer. Okay, okay, fine. So this will be the integral from FA to FA plus delta, and then you will have phi of x, and then you will have rho compose f minus 1. And this you have to choose some branch according to which integral you are, of x divided f prime of x. Sorry, f prime of f minus 1 of x, and then you get dx. Okay, so that's how things move. And then if you call this stuff rho 1, you can check that if A is large enough, rho 1 also satisfies this inequality. So it means that if you have a density that has some smoothness, the dynamics, since the dynamic is stretching, try to stretch it, and then it's true that there is this factor here that messes things a little bit, but it's clear that the derivative, these points are closer, right? Because if you look at now this ratio with respect for this guy, for this rho 1, then if you take 2 points, you go with the inverse dynamics, and so they get closer. So here you will get 2 points that are closer, so you gain something, then you lose something because there is this thing in between, and you get something, something of this force. Rho 1 x over rho 1 y is less or equal than E lambda minus 1 A plus B x minus 1. These come from the fact, we'll close this come from the fact that you have this piece down there. And now, if A is large enough, this is smaller or equal than E A x minus 1. Sorry? A is some constant that has to do with the second derivative of the function. You have just to do the computation. It's just a second derivative. So you see, so this is one fact, and now you have that there is a problem, but because you want things that are more or less of size delta, okay, and this is bigger, okay, so you break it up in 2 pieces, okay. So you can write this as alpha, the integral from from I to bi, sum over I, alpha I, of phi rho I. Well, this one is still a standard pair. Sorry, there is something that I forgot to tell you. These are probability measures, so, okay. So once you do this is not necessarily, this is still a probability measure, but if you break it up in smaller pieces that are more or less of length, bi minus ai is in the interval delta, let's say 2 delta, okay? So you want measures that are done on integral delta to delta, then of course you break it up, this is not a probability measure anymore, you normalize, this is the renormalization, so it means that sum over I, alpha I is 1. So this is just a convex combination of standard pair. So the point is that you take a standard pair, you push it, you get a standard combination, a convex combination of standard pair. So there is some invariance. This set of measures is invariant under push forward, and so you can just work only in this space. And if you take delta reasonably small, then this in some sense is conditioning, right? Because you can say, okay, I have First of all, you can take your measure and, of course, decompose it in sum of standard pair, because you just break up the interval and that's it. So you start from a standard pair, let's say AB, phi compose Fn time rho, and now this is going to be equal to the sum from I to n, some sum of some k of alpha k, phi ak bk rho k. Okay. And this pieces, it works like this. You have this A, and then it will get bigger, okay? So now it is breaking in 3 pieces, and now at a certain point, you know, they overlap, right? Because we are on the torus. So you should think of, you have a lot of pieces. As you go on, you have more and more pieces that come, an exponential number of pieces, because the length is lambda to the n. So if you break them in pieces of length delta, then you have lambda to the n pieces. So you have a lot of pieces, but now you can specify a trajectory. You can say, well, first I was here, well, I start from there, and then maybe I was there, meaning that I just belong to this guy, and then I just belong to this guy, I belong to this guy, I belong to this guy, I belong to this guy. So you just specify which standard pair you have visited in the process, and when you are here, you are still in a measure that is legitimate to start again, because these are measures that are very nicely behaved under the dynamics. So you can condition, so not exactly saying, well, I am visited this point, but you can condition with a mistake delta on the past, and you find yourself at present having specified the past, all the past with a precision delta, and you still find that you are distributed with a perfectly reasonable probability distribution that you can use to start with and do consideration on the future, like if you start with the probability distribution. So you keep the randomness in the system doing like that. So this is just a systematic way, and it's a little bit tricky, right? Because it's not really a sigma algebra, so it's not like condition. Maybe you can transform it in a sigma algebra in this very special case, but in general, these things, they overlap, they do strange things. So you cannot really transform this into the normal language of probability of a sigma algebra, but morally, it's the same idea. So just specify some history in this standard pair language, and then with that you can just do conditioning and you can work on this type of thing. So I think that that's enough for today, and I think that what I want to say tomorrow is try to answer a little bit of this complaint that I got, that this is not invertible. So say something about the invertible case. And maybe since my original motivation was that I wanted to understand a little bit better this mechanism in the Lorentz gas, then there is a thing that is, and also I had this ambition that maybe one would like to see interacting case. Then you see, if you are looking at a situation in which you have several systems, Hamiltonian systems that interact, then you have an issue that here is completely non-present, which are locally conserved quantity. And if you want to look at the physical system, typically it's inevitable to have locally conserved quantity. And what will happen is that this locally conserved quantity will evolve on a time scale which is much slower than the other degree of freedom. And so I would like to say a few words about a model in which there are these two time scales and how this machinery can be applied in order to get something in this model. Okay, but it will be a little bit more, with a bit less computation today. I did a lot of computation, so at least for my standard. Thanks a lot.